Assalamu alaikum wa rahmatullahi wa barakatuh. Peace be upon you all and welcome to the channel. In this video we will continue with the stack memory, particularly the stack frame, and this will be inshallah bi'idhnillah and God willing the last episode for the stack memory subseries, unless I decide to divide the stack frame episode into multiple videos. We will see how it progresses today. I also apologize for the hiatus, but I was rather indisposed the past few weeks. But thankfully I have enough time to continue with the recording, because as you know, the zakah for knowledge, I guess you could translate it to the tax for knowledge or the charity of knowledge, is to spread it. And I try to beg for forgiveness for any action I have undertook or will undertake in the future through these videos, because as you know, when a person dies, their actions end except for three particular actions. One of them is providing beneficial knowledge that is helpful to people, and that is why I have this channel. Now, before we begin, بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه ومن تبعهم بإحسان إلى يوم الدين وارض اللهم عنا معهم أجمعين اللهم آمين. اللهم صل على محمد وعلى آل محمد كما صليت على إبراهيم وعلى آل إبراهيم وبارك على محمد وعلى آل محمد كما باركت على إبراهيم وعلى آل إبراهيم في العالمين إنك حميد مجيد لا إله إلا أنت سبحانك إني كنت من الظالمين. We begin in the name of Allah, the most merciful in this life and in the hereafter. We thank Him for all of His blessings that He has bestowed upon us, for they are innumerable. And we pray that we follow in the footsteps of Prophet Muhammad, peace be upon him, and his fellow companions. Amen. We also ask for prayers and blessings to be bestowed upon Prophet Muhammad, peace be upon him, and his family, as they were bestowed upon Prophet Ibrahim, peace be upon him, and his family. Now, if you recall, we covered the call stack last time, and we mentioned that the call stack basically holds or stores the order of method calls in the data structure known as the stack. Hence why the stack memory is a data engine, because it is part of the memory that implements a particular data structure. And we showed that the data structure is loaded at the bottom here, and then you keep, and excuse the pun, but you keep stacking and stacking until you reach the end of the stack. So you add from bottom to top, but you remove from top to bottom. And that is the call stack. So and within the call stack, for every single method or for every single block within the stack, the call stack, is the stack frame that houses information pertaining to one particular method. Okay, so we will remove this now and discuss the different sub-compartments of the stack frame. There are three sub-compartments within the stack frame, and let us see here and here and here. Okay, the first sub-compartment is known as the operand stack. I may have mentioned this previously, but this is heavily related to assembly language, so we will not discuss it fully, but rather we will discuss it briefly to fit into the focus or into the scope of this lecture, or rather this entire tutorial series. but inshallah bi'idhnillah and God willing, if I am destined to create a tutorial series for assembly language, we will definitely discuss operands in greater detail. The second subcompartment is the one known as local variable array, also known as LVA, and you can probably infer the purpose of this subcompartment from the title. It stores the local variables of each method, and as you know, method parameters are considered local variables. I did see people refer to it as OS, but I am honestly hesitant about writing that abbreviation because you may confuse yourself and think it is operating system. Lastly, we have frame data, which is abbreviated to FD. There we go. So these are the three different subcompartments within the stack frame. So within the call stack, a particular method is added to the stack or pushed onto the stack. Then once that method occupies the stack frame, different information related to that particular method are stored or subdivided into these three areas here. Let us start with the simplest one, which is the local variable array. The local variable array compartment is responsible for storing the data pertaining to any and all local variables within that particular method. Stores data pertaining to local variables or method parameters, because remember, parameters are considered local variables. Stores data pertaining to of methods in an array. That is how the data is stored. It is stored in the format of an array. So you will have an index for every particular local variable. So the first local variable stored will be index 0 and so on and so forth, as we have discussed in the arrays lectures. Yeah, just push it like here. Possibly push this here of methods in an array. There we go. And that is it. It is as simple as that. Any local variable for a method, whether it is an actual local variable or a method parameter, is stored here. That is how the stack memory has access to local variables through the stack frame, which contains the local variable array. Now remember, and we will discuss this later when we tackle the heap memory bi'idhnillah and God willing, a local variable can either be primitive or reference data types. And remember, with reference data types, they will always be stored in the heap memory, but the address of the variable in the heap memory is stored in the stack frame here to refer or to reference the object in the heap, hence why they are called reference data types. So remember that a local variable can be a reference data type, but instead of the actual object being stored here, the address of the object within the heap will be stored here. Okay, what is next? We have frame data or frame data. This is simplistic, but we will not see its effect fully until we tackle exceptions, because that is what is stored in the frame data. Any information related to exceptions or the exceptions of a particular method. So we will write this here and say, maybe I can push this downwards like so and write it here. Stores data pertaining to exceptions thrown by the method. So basically anything within the catch block. What is the catch block? We will discuss it later, worry not, بإذن and God willing. But if you recall, when we tackled, I believe it was the reflective API, we passed by certain exceptions. What are exceptions briefly before we tackle them later on, بإذن and God willing? Exceptions are issues that arise within a particular method or within the code that you have written because of a particular mistake that you committed. I do not wish to say error, and you probably have inferred that I am avoiding the term error, because in Java, errors are different from exceptions. Hence why I do not wish to use the term error to refer to an exception, even though linguistically speaking, an exception is an error. But programmatically speaking, an exception is different from an error in Java. Because in other languages, such as JavaScript, if I recall correctly, their exceptions there, the exceptions in JavaScript are actually called errors. But in other languages, there are exceptions and there are errors, so I wish to create that distinction. Lastly, we have the operand stack. What is the operand stack? It is the stack responsible for, well, containing information about the operands. What are operands? Briefly speaking, in assembly language, we have seen a simplistic example of, or a simplistic simulation of assembly language before, where we have seen the instructions in assembly language differ from the instructions in Java because they tackle every single step the processor must undertake to execute the program fully. These instructions operate on or perform a certain action on what is known as an operand. For example, 1 plus 1. This is an operator. Why is it referred to as an operator? Because it operates on operands. So in Arabic, for example, in grammar, we have what is known as fa'il and maf'ul bih. Fa'il is the one that undertakes the action. Maf'ul bih is the one that suffers the action. In English, it is known as accusative and dative or dative, however you wish to pronounce it. That is the operand. The operand is the dative or the maf'ul bih, or the one that suffers or endures the action. Whereas the operator is the fa'il or the accusative, the one who performs the action. So these instructions operate or perform a certain action on operands. So these bytecode instructions or assembly language instructions have their own stack. Think of it as the call stack for the bytecode, or the call stack for the assembly language. So technically speaking, the call stack for methods serves no purpose other than to store the actual call stack, because that is where the instructions are truly installed or stored, sorry. because remember, the instructions in Java are not the instructions that the computer reads. The computer reads the instructions in machine code, which are directly translated from assembly language or byte code. So, for example, 3 lines of instructions in Java could equate to 6 lines of instructions in assembly language. Those 6 lines will be translated to 6 lines of machine code or binary code. But again, since this is directly related to assembly language, we will not delve too deeply into the different forms of operands available, because I am trying to limit the scope of this course to Java, and it is a beginner level, though even at advanced level I do not think we will see what happens, inshallah bi'idhnillah. So here we will say stores the call stack for the instructions within the byte code. Now let us tackle, so I guess we will not need a new video, another episode to discuss the stack frame. We finished. These are the main 3 subcompartments, and we have seen how what each compartment stores. Now let us construct a program. We may skip this part, but we will see what happens. Let us construct a program so that I can show you where once the call stack is initiated and the methods are added to the call stack, where each piece of information will be divided to. So I will resort to Notepad, mainly because I can save this wherever I want, whereas in IntelliJ it has a certain directory and I do not wish to change it because it is quite a hassle. So I will create a class called main. So this will be where the main method is. Public static void main, and I need to add the argument args. So now let us pretend this a certain algorithm within the main method throws IO exception. Just as an example, we will tackle this in greater detail later on, bi'idhnillah, and God willing, especially when we start Java IO and file IO, how to read from a file, create and save a file, and so on and so forth. That way, if you are designing your own game in Java, you know how to create the save functionality and the load functionality. Also, the serialization will help, which we will leave at the very end of this course. Say int a is equal to 5. Int b is equal to 10. Or actually, I will create another method just to have a dense call stack. We will return an int here. This will be a rather dumb method. We can say add, just for simplicity. And we will add here int num1, int num2. And here we will say return num1 plus num2. So here we can say 10. Int c is equal to add a, b. And then we will have a print statement. like so. Print C, sorry. Oh, before I forget, for the operand stack, so I will add a hyphen here. This is also stores the return address of the method. I forgot to mention that. I apologize. Every method has a return address. What is the return address? Briefly, when you have multiple methods within the algorithm, once the method finishes execution, the program or the CPU must know where to return to once this method elapses. For example, when the Java virtual machine or the processor execute this method, they move on to this block to execute the code here, because the code is available here, not here. Now, once this is fully executed, the program needs to know how to return to the next line here. So a bookmark or a placeholder must be added once the execution of this method has begun. That way, so for example, let us say the address here is, let us give a hexadecimal number, 105. That is the memory address where this method is stored. Now, once the CPU learns of the code for this method and executes the code of this method, it needs to learn, or it needs to know how to, or rather where to return to continue with the main method, which is here. It needs to return here. So how will it know that? Through this bookmark. So this return address informs the CPU, this is where you left to execute this code. Now return to this again to continue execution. This is known as the return address. It basically acts as a bookmark for the CPU to learn where to return to continue the execution of the program after it departs to execute a particular code of a particular method. So every method has a return address, even if the return type is void. There is a difference between a return type and a return address. Since this method exists in the code, it will occupy memory, which means that it will have a return address. Simply because it returns nothing does not mean it occupies nothing. It does occupy space in memory. It simply does not return anything. That is the difference. So every method has a return address, and this simply assists the CPU in identifying the proper location to return to continue with its execution. This, of course, becomes more apparent and becomes clearer when we tackle assembly language because then I can actually show you how the return address functions. But for now, simply know that once a method is being executed, the main method is put at a halt until this finishes execution. Then the CPU must return to the main method, but at the right line. It cannot return from the beginning again and resume execution. It must return where it left off, which is the return address. So the CPU executes this, then executes this, then executes this, so it has to leave the main method for a while to learn the code of the add method, execute it or implement it. Then it must know where to return to store the return value. So it must return here, it identifies the bookmark or the placeholder, stores the return value in this variable, then continues from downwards. It does not return from the beginning. If the CPU is lost during execution, it means that whenever it encounters any method, it will have to restart the main method from the beginning, which is of course hectic to say the least. Okay. So now that and the reason it is stored in the operand stack is because this is related to assembly language, as I mentioned, and assembly language handles the return address of methods. Okay, so let us save this program, then discuss it from the perspective of the stack frame and the call stack. Save as, I will save this as main.java. Remember, the name of the class must match the name of the file. Okay. Now, let me, so I have it here. Let me compile this so that we have the bytecode. So it will be Java C main throws. Okay, cannot find symbol throw. Okay. See, we already have an issue. This is why I love using IntelliJ, because it alerts me to these issues. Stay in light mode. Okay. Let us say throws exception. And then save it and try to, oh, did I close it? Try to compile it once more. Java C main. Okay, perfect. Now then, Java P v main dot class. Ah, perfect. So I have what I need here, so I will minimize this for now and then return to this one and this one. So let me move to the right side here. And what is this blurry pixel? And bring this here like that. Okay, so what I will do is I will take a picture. That way I do not need this to be open anymore. Grab this, copy it, and paste it here like so. Then I can close this. I no longer need it. Okay. Now remember, the stack memory or the call stack always begins with the main method. This is an extremely important method. You cannot start the program without the main method. You can create other methods, but without the main method you cannot execute these other methods you have created. And I forgot that I need to remove this part and drag this a bit closer here. Okay. Now, the JVM has compiled this, and we have the class file or the bytecode. So we will come to the operand stack in just a moment. Let us tackle the easier parts, which are these two. Then we can return to the operand stack. We have the main method, so let us construct the call stack. I will call this call stack. So what is the first method that is pushed onto the, let me design built-in blocks already. What is the first method that is added or pushed onto the call stack? It is the main method, like so. Now, once this is added to the call stack, here is what happens with regards to the subdivisions. The main method has this local variable, a string array known as args. So this is stored in the LVA compartment. How about I can create a subdivision within the stack frame, like so. So we need 3, one for the operand stack, one for the LVA, and one for the frame data. So this is stored within the hold on, let me adjust this a bit. So I will put it here, then build the compartments around it. There we go, beautiful. So this is added to the array. What else is added to the array of local variables? Int a is a local variable to main. How do we know? This variable is present within and only within the main method, as you can see from the curly braces. It is not present anywhere else. If it was present within the scope of the class, it becomes a global variable, but here it is a local variable. So this is stored here, and this is stored here. Then it is time to execute this method, which means that this method will be added to the call stack now. Add, like so. So we will add, pun intended, like so. And then we will create the subcompartments once again. Like so. By the way, here, this is the frame data. This is where this exception will be stored. This basically informs the JVM that the main method can induce or provoke or trigger or cause this exception. That is basically what the frame data is for. You know what? I will extend this. There we go. Yes, like that. And then I will place it like here. And then do so like here. I apologize for that. I just love everything to be neat and organized. There we go. There we go. And then we can add this subdivision and this subdivision. Okay, so now we can add this exception here. The subcompartments are divided in the same order as these three. So the operand stack is to the left, then the local variable array, then the frame data. So now add has occupied space in the call stack. What are its local variables? We have two here, num1 then num2. Well, technically it is num2 then num1 because it is from right to left. So let me organize that. Num2 then num1, like so. And then they assume the values passed to them here, so 5 and 10. This is equal to 5. Let me borrow this. There we go. and then borrow it again here, and then add 10. Now once this is executed, if you recall, and it does not have any exceptions, we can cover the operand stack in just a moment. Since it's finished execution, what happens? Now this is added to here as a local variable. With its new value, which is the addition of A and B. So it will be, let me see if I can. This requires a bit of subterfuge. And here, drag this, but remove transparency. There we go. 15. And as you recall, this is now popped off of the stack or removed from the stack. Then we will add this back into the stack again, and C here will be the local variable for that, and so on and so forth. So, and then once we reach the end of the main method, this no longer serves a purpose because it is occupying memory for no particular reason, so it is popped off. And that is basically it for the stack frame, as you have seen. Now let us observe the operand stack for the sake of clarity. But I apologize in advance if it is not as clear as it should be. Again, this is related to assembly language, which is beyond the scope of this playlist. But I will try my best to explain it within the scope of Java. Okay. Now, let us return here. So what I will do is I will take an image of that and put it here. That way it is easier for everyone to read. Okay. So we have method and another method here, and we have method and method here. Okay. So we can okay. I'm just trying to see what I will be taking and what I will be ignoring. Okay, so I will take this, paste it here. Oh man, that is large. Okay. And I will also, no, not this one. I will take this one, the main method, and that will be it. Okay, and I will place it here. And oh wow, it fit perfectly. Not perfectly, but it fits. Okay. And I will redesign this because I will probably need a larger space. So yeah, here, and I will call this the call stack. The call stack, there we go. Okay. Now let us see what happens with respect to the operand stack and the bytecode so that you can clearly see what happens within the JVM during execution. Okay, so we will add the main method to the stack frame, so it will be a rather large stack frame here, And I will write the main method here so that you know that we are tackling the main method. And within the main method, I will create a call stack, but for the operands or the bytecode. So this will be the operand stack. So I will create it in red. I will try my best to have it as large as possible. Remember, it is called a stack. So it functions exactly as the call stack or as the stack data structure. What is added is always added from the bottom to the top, and what is removed from the top to the bottom. So it obeys the laws of the stack data structure. Okay. What is the first operand added to the operand stack here? So if we look at the main method, we have this first instruction, iconst 5. What is iconst 5? It corresponds to this one. Now remember, I told you this is referred to as a constant with regards to the phases of compilation. It does not refer to the final keyword constant where this value never changes. No. Constants are particular, how should I put this? A constant is a term used during the designing process of a compiler. So this is referred to as a constant, this is referred to as a constant, and so on and so forth. But these values can change. I can set A to 6 later on in the code if I want to, but 5 remains 5. That is why it is referred to as a constant. So we will take this iconst 5. These of course are instructions for the JVM. This is the assembly language of the JVM as opposed to the assembly language for the actual processor. So this will be the first item added to the stack or pushed onto the stack. Let us see what else do we have. Then we have another instruction, iStore. Feel as if I stepped into an Apple store. We have an iStore here, so this is the second item added to the stack. And then we have by push with the value 10. I do not wish to explain all of this because, as I mentioned, this is beyond the scope of this tutorial. So let us stop here for now and see what happens. Honestly, I am unfamiliar with the assembly language instructions for the JVM. I do not recall if I attached that book or not. Oh, I did not find it. That is the problem. I have to search for it, then provide you with the book that contains the details of every instruction, of every bytecode instruction, that is. So now we have iconst 5. So we created a variable with the value 5. Then we stored it into the call stack. So let me just create the stack frames for these, like so. Now, once these instructions are executed, so firstly you have a constant, it is 5, then store it. Store it where? In the stack memory. So then we will have the array, we will have the local variable array, and I will create the array vertically instead of horizontally just to match the size I have here. Normally when I create arrays, diagrammatically I create them horizontally, but because of the lack of space I have, I will instead create it vertically like so. Here, and then we will add this one right here. This is of course is added, but I want to match the instructions so that it is easier for you to visualize. So this now occupies space in memory thanks to these two instructions. So now I will add this separation here. Now once these two have fulfilled their purposes, they are popped off of the operand stack like so. This of course is cleared, these frames are cleared, but this remains of course. Then the instructions for B, which is store the value, create another variable with the value 10, then store it in memory, and so on and so forth. Then this is for C. The loading here is to load them from the stack memory to the register for the addition. So here they are being added together. And so on and so forth. This is basically how the operand stack functions. I do not wish to delve too deeply into it because, as I mentioned, it is related to assembly language. The reason I took a picture of this, because this is the add method. As you can see, it has its own bytecode instruction list or operand stack, as you can see. Now here is a question for you. Why does it start with 0 here for iLoad, whereas here starts with 1? Remember when we mentioned that the local variables are stored in an array? That means this is index 1, so this is the second element of the array. What is the first element? It is the argument itself, the args argument. That is the first element of the array, index 0. That is why this variable here is iLoad1, not iLoad0, because this is the second element of the array. I did not add it here simply to coincide with the bytecode instructions, but technically speaking, this should be, you know what? For the sake of correctness, I will add it like so and place the first element of the array in its correct spot here. I simply wanted to isolate what was necessary for the operand stack. Then these are added onto the operand stack, and once they are resolved, int b will be added here, and so on and so forth. So the order by which the data are stored in the stack frame begin with the operand stack. Why? Because the operand stack contains the actual instructions that the CPU will undertake. Once the CPU undertakes certain instructions, they manifest in the local variable array, and once they serve no purpose, they are popped off of the stack, and then newer instructions are added to the stack, and so on and so forth. So the local variable array does not begin until the operand stack begins. And with regards to the frame data, it contains the type of exceptions triggered by this method or triggered through this method, which you will find in either the throws or in the catch block, and we will discuss what are catch blocks and what is the throws keyword later on, bi'ithnillah and God willing. Hopefully, inshallah, I can find that book that contains the list of different bytecode instructions and their definitions, because they are different. If you are familiar with assembly language, these instructions are slightly different than the instructions of other assembly languages such as x86 or Motorola. which I believe was, what was it, 68 HCS 12, something like that, I do not remember. And that is it with regards to the stack frame. Inshallah bi'idhnillah, and God willing, in the upcoming episodes we will cover the PC register, the heap, and the class or the method area. Those all I foresee will only require a lecture for each topic. None of them will take longer than that, thankfully. Then after that we will continue with the execution engine, so the JIT compiler, the interpreter, the profiler, and the garbage collector. After that we will end the architectural portion with the native keyword, the native language, the native stack, the native library, and the Java native interface. Then we can return to object-oriented programming, bi'idhnillah, and God willing. I hope this lecture was helpful and beneficial to you all. Enjoy the rest of your day, everyone. Be safe, take care, and peace be upon you all. Wassalamu alaikum wa rahmatullahi wa barakatuh. Allahumma salli ala Muhammad wa ala ali Muhammad kama sallaita ala Ibrahim wa ala ali Ibrahim wa barik ala Muhammad wa ala ali Muhammad kama barakta ala Ibrahim wa ala ali Ibrahim fil alamin innaka hamidun majid.